In terms of just a quick recap what we done yesterday morning, where I showed you this really cool trick with this dimensional analysis where you are guided by the units in your calculations. And just a quick recap. Let's say I have a substance with a molecular mass of, say, 270 gram per mole. And I want to know how many moles are in 9 gram. Right? Do you want to try it yourself? Very quickly, before you fall asleep after your lunch? Please feel free to talk to each other, convince each other that your method is right, and you can do it with whatever method you like. Sorry? You can't remember how you did it last time?
No, it was when you were saying like different levels of abilities and things like that, I was thinking like when I actually learned how to do this was back in 2003.
Oh well. So how are we going to tackle that? First question is, what are we looking for? What's the unit that we are looking for? Mole. Do we have mole anywhere? We have it in here. It's just written so that the mole is down. We want it up. So what we do is we just simply say mole in 270 gram. Which is basically the same thing. It's 270 gram is equal to 1 mole, or 1 mole in 270 grams. So we can write it like that. So we are all right with our unit. We have the mole here. That's good, in the right position. But we have the pesky grams. So we need to try and get rid of these grams. And the way we do that is we arrange it so that the grams cancel out. Do we have any grams to cancel? It is the 9 gram times 9 gram. What happens to the grams? They cancel out. What's the unit that's left? Mole. And that's exactly the unit that we want. So we can stop faffing around. And all we have left is 9 mole divided by 270. And that is 0.033 mole. Is that right? Or if we really want to, we can move the decimal 1, 2, 3. So that would be 33 millimole. Okay? Happy with that? Simples. Now let's do a little bit of some new stuff, because we have spoken so far about amounts of substance. And we said in terms of amounts, we can talk about grams, we can talk about kilograms, we can talk about micrograms, we can talk about moles, because mole is just simply a number for a certain amount of molecules or atoms or entities. Yeah? But usually we are not just concerned about the total number of these things, about the amounts. We are very often concerned about the volume in which these amounts are. So when we bring in the volume, then we talk about something different. And when we bring in the volume, we are talking about what is called concentration. And a concentration is nothing else but just simply a given amount in a given volume. Yeah? So I can, for example, say the concentration of students in this room is about 250 students per 100 cubic meters. So the cubic meters is the volume, and the 250 students is the amount. Make sense? Pretty trivial. What's not so trivial is that very often people confuse amounts with concentration. And that is where things then easily go wrong. I don't want you to be in a position like that. So when we talk about concentration, we said we can talk about moles. So a perfectly acceptable concentration would be, for example, 1 mole in 1 liter. That means I just simply have 6.022 times 10 to the 23, remember that was the Avogadro number for a mole, of molecules or entities in the volume of 1 liter, usually water or something like that. Yeah? So that is a concentration. And because people, biochemists, biomedical scientists, are extremely lazy people, instead of writing mole per liter, they just simply abbreviate that with a capital M. So that would be the same as 1m, which means 1 molar. And in this case, it's not what you have in your mouth, the tooth. It is 1 molar, 1 mole per liter. And of course, you can have fractions of that. So you can have 1 millimolar, which basically means 1 millimole per liter. You can have 1 micromolar, things like that. Yeah? So please bear that in mind. That's this definition of 1 capital M, that's quite important. Please write it as a capital M and not as lowercase m, because lowercase m means meter. And then very often things go terribly wrong, because when you multiply meter with a volume, you end up with something to the power of 4, meters to the power of 4, And at that point, usually people wave the white flag in an exam and say, I got something really bizarre. I don't know where I went wrong. Yes, I can tell you where you went wrong. You just did not write this properly. But you wouldn't do that because I told you, of course. Very easy. Okay, are you happy with that? With this definition? Sometimes we are not necessarily talking about moles per liter. Sometimes we can use a different amount. So, for example, we can talk about grams per liter if you really want to. Yeah? For example, if we don't know how many moles there are, but we know how many grams there are, if we put, let's say, 10 grams in 1 liter, then this is a perfectly acceptable concentration, grams per liter. And just to annoy you and add a little bit of spice, very often you see an abbreviation which, or you see gram per 100 milliliter. Yeah? Gram per 100 milliliter. Especially when it comes to biomedical sciences. Very often this is used, this abbreviation, gram per milliliter. You sometimes see also, for liter, instead of liter, you see decimeter to the power of 3. It's the same thing. Yeah? Now this gram per 100 milliliter, there's a twist to it, which I want to share with you. Does anyone... Oh, no, we do it the other way around. If we have 1 gram per 100 milliliter, what do you call 1 in 100? Translate that into a different... translate that into Latin. 1 in 100. Sorry? Centimeter? You are... Centiliter? Oh, you are getting close. What is 1 in 100? Percent. Exactly. 1 in 100 is percent. Did you do Latin? No. Well, centum, 100. Centurion. You know what a centurion is? It's 2 things. Either the leader of a group of 100 soldiers, that's a centurion in ancient Rome, or if you do a centurion, it is you have 100 little shots of, well, shots. And you drink that in 1 row. I would not recommend that. People have died. So, 1 in 100 is 1%. Right? Now, since we have different units here, this here is a weight, and this here is a volume. We write 1 gram per 100 milliliter. We can write that as 1%, that's the percent sign, obviously, weight per volume. Does that make sense? Yeah? And it's quite annoying with these 100 milliliters because we are usually used to work with 1 liter. And there's a very simple trick how you can convert that. So if you have a 1 gram per 100 milliliter solution, so that's our 1% weight per volume, what we do is we just simply multiply or expand this fraction here by factor 10. So we get 10 times 1 gram over 10 times 100 milliliter. And that gives us 10 gram per 1 liter. This is a very simple conversion in this case. Make sense? Yeah? Are you still here? Good. So, one of the questions when I ask you to make up a solution in the solution quiz was how many grams of a substance do you need to make up 100 milliliter of 2% weight per volume solution? So we want a 2% weight per volume solution. 2% means 2 gram per 100 milliliter. And indeed, we want 100 milliliters, so how many grams do you need? 2. Very simple, very easy. Okay? Does that make sense to you? It's not, technically terribly exciting and challenging. You just need to know what it actually means. Okay, now let's have a little bit of fun with these things, as much as fun is the right word in this case. Let's say I have a solution here. That's my beautiful solution of something. And in this solution, I have the concentration of this solution is 0.1 mole per liter. That's the concentration. Very often this is abbreviated with C. Although I don't like that very much, because very often C can also mean the speed of light. By the way, has anyone actually measured the speed of light at school? No? You have done that? Speed of light with a microwave? Yeah. Has anyone done it else? Speed of light in the microwave. That's a fantastic experiment. All you need is basically a microwave and a Mars bar. That's a fantastic experiment. I can send you a link to that. But I'm completely, digressing. Anyway, that is our concentration. And our volume of this thing here is, let's say, 0.1 liter. Okay? So we've got 0.1 liter of a substance with a concentration of 0.1 mole per liter. And now the big question. How many moles do we have actually in here? How many moles are in there? You want to try it yourself? Or shall I show you the trick with the dimensional analysis? Show the trick? Yeah? Okay, what are we looking for? What's the unit that we are looking for? Mole. Excellent. Do we have mole anywhere? Do we have mole anywhere? We have 0.1 mole per liter. So we've got the mole already in the right position. Great. What do we need to get rid of? We have to get rid of the liters. Do we have liters anywhere? We have the liters over here. So times 0.1 liter. What happens to the liters? They cancel each other out. What's the unit that we've got left? Mole. What is the unit that we want? Mole. Voila, we can finish with it. We can stop. So we have 0.1 times 0.1 mole. And that gives me 0.01 mole. Or I can write this a little bit nicer. I can write this as 10 millimole. Make sense? So with this dimensional analysis, again, even without knowing the equation that you would need here, you immediately could solve this question just by looking for the units. For people who are really, how shall I say, who love their equations, we can also say here mole equals the concentration, that was our concentration here, times volume. That's this guy here. Yeah? If you really want that, if you want to remember that. Okay, does that make sense? So far? Any questions? Okay, good. I'm good. I'm very good. So, how many mole are in 100 milliliter of a 1 millimolar solution? Tell you what, I hand over to you guys. You do the calculation. Talk to each other, solve that problem. Okay, got it? So again, we are looking for moles. Give them a round of applause when they are leaving. So, we are looking for mole. Do we have mole anywhere? Although it's hidden. It's in here. 1 millimolar is 1 times. Milli stands for 10 to the minus 3 mole per liter. Right? So we have, let me write it here again, mole 1 times 10 to the minus 3 mole per liter. The mole is right, liter we get rid of, and we have to get rid of with this one here, times 100 times 10 to the minus 3, that's the milli, liter. Liter cancels out, and we basically have 100 times 10 to the minus 3 times 10 to the minus 3 mole. We can write this a little bit nicer. This is 100 times 10 to the minus 6 mole. Or it is 100 micromole. Yeah? Did you get that when you did the calculation? Fantastic. Excellent. Right. So we can very easily calculate how many moles we have in a certain amount of volume. Last thing. Very often we want to make up a solution and we just have a powder. Let's say we have glucose. Glucose, molecular mass of 180 gram per mole. We want to make up 100 milliliter of a 0.1 molar solution. How many grams do we need? How many grams are needed? Again, it's very simple. Do you want to try it yourself, or shall we do one example together, and then you can do basically all of them yourself? Shall we have a look at that? What do we need? What are we looking for? What's the unit? Grams. Do we have grams anywhere? Where? 180 grams per mole. 180 grams per mole. So the grams are in the right position. Lovely. Just have to get rid of the mole. Do we have mole anywhere? Where's the mole? We have it here. 0.1 mole per liter. It's our 0.1 molar. What happens to the mole? They cancel each other out. So we have grams per liter. So we want to get rid of the liter. Do we have the liter anywhere? We have it here, times 100 times 10 to the minus 3 liter. 10 to the minus 3 is milli again. What happens to the liter? Cancels each other out. What have we got left in terms of units? We have grams. What do we want? Grams. So hanky-dory. So we have 180 times 0.1 times 100 times 10 to the minus 3 gram. And if you do that on your calculator, let's see if I can do that in my head, equals 1.8 grams. Is that right? So I need 1.8 grams for my solution, 0.1 molar, 100 milliliter. Shall I tell you something? This is a question a lot of final year students struggle. In your final year, you can do a lab-based project where you are actually a true scientist, where you explore new things, where you design your own projects, where you design your own experiments, and find out some, hopefully, hot stuff. The reason why many experiments don't work is because students have forgotten how to make up these solutions. If you can do that, you are probably at that stage now better than a lot of final year students. Yeah, I see. The eyebrows go up. Yeah, how cool is that? I did that also, a little experiment with students at another university up north. And they were completely thrown. We don't know how to do that. I said, yeah, you do. You have done it in the first year. And I said, oh my God, yeah, that was in the first year. We are in the third year. We are allowed to forget everything that we have done before. And I asked them, can you still write your name? Yeah. Okay. Rest my case. Right? This is something that's absolutely essential. This is actually, when you're looking for a job afterwards, this is very often what people will ask you in a job interview. How would you make up 100 milliliter of a 1.23 millimolar solution of ATP? Here's the molecular weight. Practice, 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 practice. Okay? Last one. Very often, we don't have a powder that we weigh in. Sometimes we actually have a solution. Round of applause.
I'm not leaving, I'll be back in a minute.
Oh, okay, okay. Okay, no applause for him. Sometimes we have a solution. This is usually called a working solution. A working solution very often is quite concentrated. a concentrated solution. Can't even write properly. And we use this concentrated solution, dilute it, to get what is called, oh dear, I'm a complete idiot. It's not a working solution, it's a stock solution. I beg your pardon. We have a stock solution, dilute it, and we get what is called a working solution. Which, of course, is less concentrated. So, for example, you have 80% proof vodka. That is your stock concentration. And you want a 20% working concentration because 80% knocks you out. Yeah? So what you need to do is you have to dilute it. Very clearly. So how can we actually do that? Let's say here that is our stock. And let's say, for argument's sake, we have a 1 molar concentration stock. We want 100 milliliter of a 0.1 molar solution. That's our working solution. This is what we have. This is what we want. How are we going to do that? Sorry? Use the stock. Okay, good. But you said 10 milliliters. How did you get that?
Because then you're going to add 90 milliliters of distilled water.
You're absolutely right. Are you absolutely clear what he did? You're absolutely right. But let's do it step by step. Right? So we have to take some of the stock and put it in here. But how much do we need for that? Okay. Let's say we calculate first how many moles we actually need in our working solution. So how many moles are in this working solution? And of course, we can do that very easily. What are we looking for? Mole. Do we have mole anywhere? Look at that one. So that is 0.1 mole per liter. Yeah? Mole is okay. Liter needs to go away. Do we have liter anywhere? Where's the liter? It's up here. So we can write this as 100 times 10 to the minus 3 liter. Liters cancel out. And we have 0.1 times 100 times 10 to the minus 3 mole, and that is the same as 0.01 mole. Is that right? Yeah? So, here we have 0.01 mole in it. It's what we just calculated. Where do these 0.01 mole come from? What do you think? Where do they come from? Of course, they're coming from the stock. Yeah? So what we need to do now is we need to ask the question, actually, how much volume provides us with 0.01 mole. Does that make sense? This question. How much volume do we have, or do we need to take, so that we have exactly 0.01 mole? So what were you looking for? What is that we are looking for? Well, we are looking for a volume, in this case, liter. Do we have liters here in the stock? The unit liter. Who finds the liters? We have it here. We have 1 liter per 1 mole. So liter is good. Do we have mole that we can cancel? Yeah, it's this one here. Times 0.01 mole. Mole cancels. What have we got? We have 0.01 liter, which is the same as, of course, 10 milliliter. So what we basically have calculated is, first step, how many moles do we need here? How many moles do we want? And then we calculated in the second step, what is the volume that gives us exactly this amount of moles? Yeah? And what we basically do here is we make use of a very sort of important equation. We say the moles from stock equals the moles in the working solution. Yeah? And for moles, we've said earlier, here these moles equals concentration 1, volume 1. And here we have concentration 2, volume 2. And that should be the same. And that is one of the important equations. C1 V1 equals C2 V2. How come? what we do is, here we then ask for the volume. What's the volume that we need in order to get this amount of moles? Just to give you a quick other example, I want to have 1 milliliter of 1 millimolar solution. And I have, no, let's do, yeah, and I have 5 millimolar working solution. How do I do that? We do C1 V1 equals C2 V2. Here our concentration of the working solution is 1 millimolar. The volume is 1 milliliter. And that comes from the stock solution, which is 5 millimolar and question mark. That's not a question mark, that's an X. Question mark. So all we need to do is solve that for the question mark. Question mark is 1 millimolar times 1 milliliter divided by 5 millimolar. The millimolar cancels out. We've got a milliliter left. That's exactly what we want. And that gives us 0.2 milliliter. Again, practice makes perfect. 10 minutes comfort break. Whoever wants to go, please leave. I don't take it against you. Have a lovely weekend. For those of you who are staying back, I will do some more of these calculations to get you a little bit more comfortable with that. Back at 5 past.